Good morning to all of you. Now today I am introducing three more terms, three definitions in fact, so that you will be able to solve all kind of problems related to moment of inertia of 2D and 3D as well. So these definitions are, the first definition is equimomental particles. As it is clear by its name, that means you have the particles and you have a body. The moment of inertia of those particles about any given three axes is same as the moment of inertia of that rigid body about the same axis. That is why it is called equimomental particles. Okay. So very simple definition. The lamina and a set of particles. They are separate. Lamina is here, set of particles are here. But they have same mass, they have same center of gravity, they have same moments and products of inertia about all the given three axes, three mutually perpendicular axes. Then these particles are termed as equimomental particles. That means if a question of equimomental bodies, particles is given to you, what you have to do? You have to find the moment of inertia of that body about x-axis, and then you have to find the moment of inertia of the particles about same axis, and then you have to equate. If they are equal, all moments and all products of inertia, if they are equal, then you will see these are equimomental bodies or equimomental particles. I hope the definition will be clear to you. Now the next definition is that of momental ellipsoid. Now till now you are familiar with these capital letters, capital A, capital B, capital C, capital D, capital E, capital F. What are these? These are moments and products of inertia about x-axis, y-axis, moment of inertia about x-axis, moment of inertia about y-axis, moment of inertia about z-axis, product of inertia about x-axis. Now once I say about axis means it is summation m, y, z. X is omitted. Then E, y is omitted. Summation m, x, z. And F, summation m, x, y. All these terms we have introduced earlier and you are familiar with them. So these are moments and products of inertia about the given axes. Then the moment of inertia about the inclined line. This is also we have calculated, isn't it? The inclined line is inclined at an angle theta with the x-axis, and the direction cosines of that inclined line are known to you. You know, in 3D, if you want to specify a line, you need the direction cosines of that line. So here the DCs are known. They are given as L, M, N. So that moment of inertia is AL square plus BM square plus CN square minus 2DMN minus 2ELN minus 2FLM. This is the result we have already obtained in one of the lectures. Now, this line must pass through the origin. So let us assume that this line is OQ. Now this line turns in such a manner because that is the inclined line, inclined from the x-axis. So it is turned. It is turned in such a manner that this moment of inertia is inversely proportional to the square of the distance. That means this moment of inertia is proportional to 1 upon OQ square. And once this happens, if something is proportional, that means it will be equal to a constant multiplied by that thing. So mk to the power 4 divided by r square. A very simple question. Why we are taking mk to the power 4? It will be clear later. Okay. So that is merely a constant divided by r square. Now what we have to do to find the momental ellipsoid? Momental ellipsoid is actually the locus of that cube which is turning. Is that clear? Locus of cube. And you will see that this locus of cube is nothing but making a ellipsoid. How? Let us see. So the locus of Q will be the required momental ellipsoid. You know that this is equal to k to the power 4 divided by r square. Multiply left hand side as well as right hand side by r square. This r square is taken over here. So what will happen? L square r square, that will be L square into r square, and this we know that this OQ is nothing but r. So L square r square will be x square. L square r square will be x square, and m square r square will be y square, and n square r square will be z square. Now let us see why. LR is x, MR is y, NR is z. So here you will get L square into R square, so it will become AX square. Here you will get M square R square, so you will get BY square, and CZ square minus 2DMN minus 2E. Why MN? No, not MN. This will be 2D, X is omitted, YZ minus 2E, Y is omitted, so it will be X, Z, and here you will get X, Y. Now you are familiar with this equation. This is nothing but momental ellipsoid. So momental ellipsoid is AX square plus BY square plus CZ square minus 2DYZ minus 2EXZ minus 2FXY is equal to MK to the power 4 is equal to a constant. So this equation represents a momental ellipsoid, and this is what we wanted to define. So now we are in the position to find the momental ellipsoid, to find the equimomental particles. Now one more term is left which I will introduce now, that is principal axis. Now you can further reduce it in 2D. What will happen in 2D? In 2D, you will get only A, B and F. So you will be getting a momental ellipse. Put A, C0, E0, D0, you will get only 3 terms, and these 3 will contribute to the equation of ellipse. So that will be the result. Now let us come to the next part, the last term, which I want to introduce in order to do the number of questions. So this last part, I am going to introduce the principal axes, a very simple concept. The axes, pair of axes about which product of inertia vanishes. What is principal axis? A pair of axes about which product of inertia vanishes. Product of inertia vanishes about a pair of axes is termed as principal. So, using these 3 definitions, I am going to take number of questions next time. Okay, I hope this is clear to all of you. What are principal axes? The product of inertia vanishes about a pair of axes. That means if it is a case of 3D, then what will happen? D will be 0, E will be 0, F will be 0. Okay. So we are going to use these 3 terms, and we are going to do number of questions based on these 3 terms next time. So that's all for today. Thank you very much.